So when we analyze the running time of an algorithm or look at multiple algorithms and try to compare the running times, we usually focus on the running time as the input size grows. We don't focus on the running time for very small values. Because if the input size is 2, probably most algorithms are going to do an okay job. Regardless of whether it is exponential or polynomial or linear, it's not going to make a big difference in practice, again, if the input size is 2 or 4 or 5. The question is, as the input starts growing in terms of size, how do these algorithms and their running times start differing? Does the gap start opening between their running times and so on? So this is why when we do analysis of running time, we focus on the order of growth of the functions that are given for the running times. So if I have running times of 4 algorithms, and for each one, again, we have the function of the running time, a function in terms of the input size, what we really mainly focus on is that how do these functions compare to each other as the input size starts growing? Again, even for input size of 2 or 4 or 5, I don't really care which one is smallest or which one is biggest. I'm not going to choose an algorithm based on how it performs on an input of size 2, because when we deal with real-life problems, we are not going to be dealing with inputs of size 2. In real-life problems, we are going to be looking at inputs of very large sizes most of the time. And it matters to us how is the algorithm going to perform when the input size gets larger. And this brings us to the concept of growth of functions. How do they grow? To illustrate this, I'm going to imagine a scenario of having a problem, one problem, for which four different algorithms, A, B, C, D, were developed. Okay? 4 students developed 4 algorithms for the same problem. I'm going to assume all of them are correct. And I will look at the running time. I asked the students to analyze the running times of these algorithms. They came back to me. The student developed algorithm A said his algorithm runs in log n. Okay? It's a log of n. A student who came up with algorithm B told me that her algorithm runs in linear time. It takes O of n time, or in the order of n. The third student told me that the algorithm runs in n squared. And the fourth student told me that her algorithm runs in 2 to the n time. Okay? So here on the board, I'm showing a table illustrating these 4 functions of running times, that for the 4 algorithms A, B, C, D, again, one algorithm takes log n, the other takes n squared, 2 to the n. And I want to look at how these functions grow. Again, as I said, for small input, it's not going to matter. Any algorithm I choose is going to be fine, probably. The question is, how do these algorithms start differing in terms of running time as the input size grows? So to look at that, or to answer that question, I will do a very simple exercise. I will try just a few input sizes and see how the functions evaluate too. So I'm going to try 3 input sizes, 2, n equal 2, n equal 16, n equal to 56. Again, let me remind you once again that even 256, which is much larger than 2, this is still very small compared to sizes of inputs in real-life problems that we solve computationally. So these, by any standard, these are still very small input sizes. But for the sake of the exercise of looking at how these 4 algorithms are going to fare in terms of running time, it is sufficient to look at these numbers. Now, for each one of these numbers, I'm going to evaluate the function, the running time function for all algorithms. So if the input size is 2, algorithm A is going to execute 1 operation, B is going to execute 2 operations, C is going to execute 4, and D is going to execute 4. With today's computers, and even with computers from 20 years ago, these are not going to make any difference in practice. Okay? 1, 2, 4 operations, regardless of the algorithm, and the machine is going to execute them. You hit enter, you get the answer immediately. I go to input of size 16. Algorithm A is going to perform 4 operations. B is going to do 16 operations. C is going to do 256 operations. D is going to do 65,000 operations. With today's computers, these algorithms, 65,000 operations, or 4 operations, the algorithm is going to terminate in fractions of a second. Okay? So the input size increased. The running time started increasing. D is the largest. A is the smallest in terms of running time. But still, we are fine, okay? I mean, it's not a big deal to run an algorithm that takes this many operations because, again, today's computers can do this very, very quickly. Again, this is going to be fractions of a second. Now let's look at the third input size of 256. We go to 256. Algorithm A performs on the order of 8 operations. Algorithm B performs on the order of 256 operations. C is going to take on the order of 65,000. Now algorithm D is going to take on the order of 10 to the 77 operations, whatever the name of that number is. I don't know if there is a name for such a number, but it's going to take on the order of 10 to the 77 operations. Okay? Now we start asking questions. Okay? Now input size is 256. These differences here with today's computers are not significant. Again, yes, 8 operations is going to be faster, but 65,000 operations is going to still be fractions of a second. How long is it going to take to do this? Okay? How long is it going to take to do this? So this is the number of operations that this algorithm is going to perform. Okay? So let's just make some simple assumptions, and let's assume that I have a very powerful computer that can do 10 billion operations a second. 10 billion operations a second. So now I ask, how many seconds is this going to take, or how much time is this going to take? So if I can do 10 billion operations a second, I can divide this by 10 billion, will give me the number of seconds. I can divide that number then by 60, it's going to give me the minutes. I can divide that number by 60, it's going to give me the number of hours. I can divide that number by 24, it's going to give me the days. And as I divide that number by 365, it's going to give me the number of years. If you do that exercise, you will find that even if your computer can deal with 10 billion operations a second, this is going to take on more than 10 to the 59 years. Okay? It's going to take more than 10 to the 59 years. That's if we assume that the computer can do 10 billion operations. Okay? Now, 10 to the 59 years, there are 2 issues. First of all, to the best of my knowledge, the laptops and desktops that we use today cannot do 10 billion operations a second. This is number one. Second thing, 256 is still very small for an input size. So in practice, we will be dealing with much larger input sizes. In practice, we will be dealing with computers, using computers that can process fewer than 10 billion operations a second. You can get the point. If under these simplifying assumptions and generous assumptions, I'm getting 10 to the 59 years just to handle an input of size 256, you can imagine what's going to happen in practice. Okay? So this is the sense. This is why we are interested in the growth of function. Is that I'm interested in how the running time is going to grow as the input size grows. Because this is not where I'm interested. This is not the input size that's going to concern me. What's going to concern me is that as the input size grows, how does this function grow? If it grows like this, I go from 2 to 16 to 256, and the function grows even sublinearly, right? I mean, if I draw that, if I draw the plot here, and the x-axis I put the input size, and here I put the function running time, and this is 2 here, and this is 16 here, and this is 256 here. Again, 2, 16, 256. This is a linear, suppose this is a linear function here, 2, 2, 16, 16. So this is going to be the y equal x here. This function, the log n, is growing actually slower than that, slower than linearly. The algorithm B is going to take this running time linear. The squared one, running time is squared, is going to take n squared, but 2 to the n is going to start growing very fast. This is where 2 to the n is going to happen, and this is n squared, this is the n here, and this is log n. So when I look at the growth of functions like this, in these terms, I can see that algorithm A, as the input size grows, its running time is growing. Of course it will grow. I cannot think of many interesting algorithms whose running time is not going to grow with the input size. So that's not the question. The running time is going to grow as the input size grows. The question is, how does it grow? Okay? This is a nice growth. We would love an algorithm whose growth is like this. We love an algorithm whose running time also grows linearly. We can tolerate, and we would be happy also with quadratic time, n squared. But an algorithm that takes 2 to the n is not going to be very practical. Okay? Again, as I said here, if n is 256, if you can handle 10 billion operations a second, it's going to take us 10 to the 59 years. What is the point of such an algorithm? Even if it is correct, even if it is elegant, even if it's written in whatever programming language, it's useless. Okay? So this is why we focus on the growth of functions, and they are of interest to us. Now, as we focus on the growth of functions and we start looking at running time as n becomes bigger and bigger and bigger, or as we say mathematically, as n goes to infinity, what we can do is that as n starts growing bigger, we can start focusing on dominating terms in the functions. Okay? So if I have functions that are growing, and 2 functions and have multiple terms in them, all I really need to think about are the dominating terms. To illustrate that, let's think about 2 functions, 2 algorithms whose running time. One of them is 1000n, and one of them is n squared. Okay? So we have 2 algorithms. One takes 1000n, one takes n squared. What I mean by as n goes to infinity, we can focus on dominating terms. As n goes to infinity, dominating term is going to be the n squared, not the n. Okay? How do I know that? If n is 1, of course, this function is bigger than this. If n is 2, this is bigger. If n is 3 is bigger, 4 is bigger, and so on. At some point, I will get to a value of n, after which n squared is going to be much bigger than n. That point is actually n equals 1000. When n equals 1000, these 2 are equal. But when n equals 1001, this becomes bigger. When n equals 1002, this becomes bigger. 1003 becomes bigger, and so on. So this one, after n equals 1000, this one becomes the dominant one. Okay? So if I have really a running time of an algorithm that is, let's say, 1000n plus n squared plus 7n cubed plus n to the 4th, I can simply say that this algorithm is going to be dominated by n to the 4th. This is what we mean by focusing on dominating terms and ignoring lower order terms. Further, we can start also when I look at 5n squared versus n squared, I can ignore this constant because the n squared is going to be the dominating term rather than that 5. The 5 is not going to make a big difference. Okay? So when we look at growth of function, we are really interested in running time as the input size grows to infinity. And as the input size grows to infinity, we can focus on dominating terms and start ignoring multiplicative factors, constant factors, and we can start ignoring lower order terms.